Assalamu alaikum and good morning everyone. Welcome to the 11th series of IEEE Symposium on Computer Applications and Industrial Electronics 2021. I am Annaz Mustaqib, pursuing my Masters in University Technology Synchronous in Electrical and Electronic Engineering under the supervision of Dr. Michael Drieberg and with co-supervision of Dr. Azrina Binte Abdulaziz. The title of my paper is Energy Efficient Synchronous MAC Protocol based on QoS and multi-priority for wireless sensor networks. These are the outlines that we are going to follow throughout the presentation, starting from introduction, literature review, proposed MAC protocol, protocol evaluation, results and discussion, and conclusion. For the introduction, we need to be familiar with some important topic. First, the wireless sensor networks. A wireless sensor network can be defined as a collection of small miniature devices called the sensor nodes, which can communicate and transmit the information wirelessly. The function of this sensor node is to sense the environment and collect data about different scenarios, for example, hazards, fire, physical phenomenon, etc., and forward it to the sink. There are many applications of the sensor nodes, like for environmental monitoring, agriculture, health, military, industry, and can be used commercially as well. These sensor nodes always have to rely on using small battery source which can supply electrical energy to the nodes. So these sensors are called battery powered wireless sensor networks. The lifespan of these nodes is limited. It uses non-rechargeable batteries as a power supply and they are easy to install. From the figure, we can see that the energy from the battery is directly transferred to the sensor nodes for battery powered wireless sensor networks. The next slide is about Medium Access Control Protocol and QoS. The Medium Access Control Protocol, or shortly MAC protocol, the main purpose of the MAC protocol is to provide medium sharing approach among the sensor nodes. For example, if a sensor node wants to communicate with another sensor node to share information, it has to use MAC protocol to access the medium and communicate wirelessly. The another term is QoS, or quality of service, which is the ability of giving different priorities to various users, applications, and data frame or packets based on the requirements. For the literature review, we have studied MAC protocols for battery-powered wireless sensor network. Among them, one of the protocol is MPQ MAC protocol. MPQ MAC protocol is a receiver-initiated MAC protocol which considers 4 different levels of data packet priorities. And another protocol is QAE MAC protocol. It is also a receiver-initiated MAC protocol and considers 2 different levels of priority. ERI MAC is another receiver-initiated protocol that has been chosen for comparison because it is the most basic receiver-initiated MAC protocol. We can see that these protocols do not provide any approach to reduce the energy consumption. So this protocol has the following limitation. First, the receiver has a fixed duty cycle, which can use significant amount of energy that can lead to a network failure and packet loss. Second, if the load is lower, significant amount of energy will be wasted on idle listening, and if the load is higher, then the delay will also increase. The proposed protocol is a timeout multi-priority based QoS MAC protocol, or TMPQ MAC protocol. The TMPQ MAC protocol uses a synchronized approach for the data packet transmission and considers QoS and multi-priority. It uses P-persistent carrier sense multiple access scheme, which considers an adaptive active and sleep time to reduce the energy consumption by minimizing the idle listening. So now we are going to talk about the communication process of the TMPQ MAC protocol. So this is the communication process of the TMPQ MAC. So at the beginning, the nodes wake up and start by waiting and listening. From here, we can see that all the nodes will wake up and start by waiting and listening. The nodes broadcast a sync packet if it does not hear anything for a certain time, which contains the starting time of the next frame. If the nodes receive a sync packet from the receiver node, it will follow the schedule and sends in its own sync packet. If a node has its own schedule and here's a different schedule from the receiver node, the node will adopt both schedule. After the synchronization, activation time, or TA, will be fired. and the receiver node will wait to receive transmitter beacon from the sender nodes until the timer TW expires. If it does not receive any transmitter beacon, the receiver will simply go to sleep after the timer expires. If the nodes receive multiple transmitter beacon, then based on the packet priority, a sender node will be selected and the receiver will broadcast a receiver beacon with the selected sender's address. After sending the receiver beacon, the receiver will wait for the data packet. In the meantime, the sender nodes will perform clear channel assessment or CCA to see if the medium is idle. After finding the medium idle, it transmits the transmitter beacon and expects a receiver beacon from the receiver. Once the receiver beacon is received at the sender node, it checks whether the beacon contains the sender's address. If it does not contain anything, then it will directly go to sleep. If it is selected, the sender will send the data packet and the receiver sends an acknowledgement packet after successfully receiving the packet, and the activation time TA will be cancelled. After that, the sender node directly go to sleep. If the data transmission is not completed during the activation time, and the node receive transmitter beacon or the receiver beacon, the activation time or TA can be renewed to complete the data transmission. Also, after the synchronization, the other sender nodes also synchronize with the receiver and also adopted each other's schedule. If there is another data packet waiting to be sent by a different sender, the sender nodes wake up at the scheduled time and the sender nodes will send their data packets to the receiver. If there is no activity during the TA will be cancelled. The receiver will directly go to sleep. After receiving all the data packets from the sender nodes synchronized with the receiver goes to sleep and ends the first round. So all the nodes will send the data packet for in each of their frame, and after completing the data transmission, it will directly go to sleep, and the receiver will ends the first round. So from here, this we can see that the sender 1 is sent in frame 1, sender 2 has sent in frame 2, sender 3 will send in frame 3. Since there is no there is no activity in the frame 3, so the receiver will directly go to sleep after hearing nothing for a certain time, and the activation time will be cancelled. After each round of data transmission, the receiver will go to sleep. This slide shows the multiple rounds of data transmission where the receiver node goes to sleep after ending each round of data transmission. So after completing round 1, the receiver will directly go to sleep. After then it will again wake up for round 2, and completing round 2, it will directly go to sleep, and it continues. So the performance of the TMPQ MAC protocol has been evaluated using the Castalia simulator. The simulation parameters for the proposed TMPQ MAC protocol are given in this table. So in this network, multiple senders transmit the data packet to the same receiver, and all the senders are within the communication range of the receiver. In the simulation, the network generated a total of 10,000 packets, where the size of each data packet is 28 bytes. So from here we can see all the simulation parameters that has been used for this simulation. So for the results and discussion, the average end-to-end delay of all priority packets is shown in this figure. The result shows that the delay of P4 priority packet of TMPQ MAC reduces up to 6% over MPQ MAC. So the P4 packet of TMPQ MAC is in blue. From this curve we can see that. So it reduces 6% over the MPQ MAC. It can also be noted that the TMPQ MAC protocol sends the P4 priority packets with less delay when compared to the highest priority level for QAE MAC, which is it is P2, and for the ERI MAC, which is P1. Since there is only two priority for the QAE, and there is no priority for ERI MAC. So we can say that TMPQ MAC shows better results over the other protocols. So from here, that we can see that the TMPQ Mac reduces the energy consumption at any number of sender nodes, and because it has adaptive, active, and sleep time. The TMPQ Mac provides 7.8% improvement over MPQ Mac and QAE Mac, and 8.6% improvement over ERI Mac. Therefore, we can say that TMPQ Mac performs better when compared to the other protocols. The results of average end-to-end delay for all packets is shown in this figure. It can be seen that the average end-to-end delay for the TMPQ Mac shows an improvement of up to 3.5% over MPQ Mac, and since it can reduce the idle listening, and 7.9% over QAE Mac. So TMPQ Mac shows better results over all the other protocols here. So now this figure shows the average throughput, which can be defined as the total packet received per second. The results show that as the number of sender node increases, throughput increases linearly, and the proposed TMPQ Mac provides same performance as compared to the other protocols. Now, this slide is about the packet delivery ratio, or PDR, which can be defined as the total packets received by the receiver node divided by the total packets sent by the sender nodes. The proposed TMPQ Mac and the other protocol provides 100% packet delivery ratio for any number of sender nodes. So the results show that the TMPQ Mac protocol and the other protocol gives the same performance, which is 100% for the PDR. So for the conclusion, this paper proposed an adaptive energy efficient synchronous TMPQ Mac protocol based on the QoS and the multi-priority to achieve low energy consumption and minimize the packet delays for wireless sensor networks. So TMPQ Mac adapts listen and listen. So the TMPQ Mac adapts listen and sleep time dynamically in a way that it can extend and end the active time, which reduces idle listening and energy consumption. The results show that the performance of the proposed protocol outperforms the other protocols and significantly improves average energy consumption, average end-to-end delay for priority packets, and the average data packet delays. So thank you so much for listening. If you have any question, you can comment on the YouTube section. Thank you so much.